Hi everybody, welcome to this tutorial on binary trees. Today we're going to look at how to insert a new node into a binary tree. Now, before we get started, I just want to explain, if you have been following this course, you should already be familiar with the algorithm for searching a binary tree for a specific value. And what I've done here is created a function which runs that algorithm, and it returns the index of the node storing the search value, or of course -1 if the search value does not appear in the binary tree. Okay, so you might want to take a moment to look at this algorithm and see if it makes sense before we look at inserting a node into a binary tree. I just want to make clear that this algorithm is not essential to today's tutorial, but we will be using this function later, and we'll look at that towards the end of today's tutorial. So what we're going to do today is design a new node. Let's just give it some data and a left pointer and a right pointer. I am following the design of the node class, which I've got here. The first parameter is the data, then the left pointer, and then the right pointer as we construct a node. I also want to state, maybe I should have said this before, in my design, I have a binary tree which stores 8 nodes. These 8 nodes are these 8 nodes. We're just going to use this as an example. So first of all, I developed the individual nodes. So node at index 0 is this one. Node at index 1 is this one. Node at index 2 is this one. So we're just reading from top to bottom, left to right. 0, 1, 2, 3, 4, 5, 6, 7. Okay? So these are the 8 nodes put in order into our array, but arranged through pointers as a binary tree. So it should work as expected. Now this new node, which has a value of 33, let's see if we can just predict where it's going to be inserted into the tree. So our value is 33. Is 33 greater than 13? Yes, it is. So we're going to go to the right. Is 33 greater than 18? Yes, it is. So we're going to go to the right. We're going to go to node 6, or the node at index 6. Is 21 greater than, is 33 greater than 21? Yes, it is. So this is where we're going to place the new node, 33. So this index number here, this right pointer is going to change. Okay, now how is that going to change? Let's see if we can figure that out. If my array storing my binary tree looked like that, we wouldn't be able to insert a new node because we don't have any free elements. But my design, I've just added on 2 empty elements to allow me to add some new nodes. Okay? So the first empty element is at index 8. This is index 8. So let's just make a note of that. The free pointer is at index 8. So I'm going to push my new node into that element. So btree free pointer will be assigned the new node. Done. So conceptually, the node is now here. If we could visualize it like this, the node is now here. But it's not yet a member of the tree, really, because we haven't updated this index. So we're going to have to produce an algorithm to work its way down the tree and see if it can find the place where this node is going to exist. So let's look at that algorithm. I'm just going to create a search pointer and assign it to the root. The root is at index 0. I'm now going to create a while loop while search pointer doesn't equal -1, we're going to find our way through the tree to get to one of these leaf nodes, which is where the new node is going to be inserted. Okay, so if the new node dot data is greater than my btree's node, which is referenced by search pointer dot data, then we're going to update the search pointer as follows. Btree search pointer dot, if the new node data is greater than, if 33 is greater than this node's data, we're going to go right. What did I call it? I called it right P. So let's use that. Else, search pointer is going to be updated to go along the left trail. Okay, so we're looking for the appropriate -1 because we want to find an insertion point. An insertion point can only happen on an empty an empty pointer in a node. So it's going to be, we're looking for -1s. Which one is it? There's many of them. Of course, we know it should be this one if the value is 33. So let's let the loop run and then let's print search pointer and see if that worked. So we're going to run that. Yay, we got to a -1. Brilliant. The problem is we know we've reached a -1, but we have no idea which element we're at. This is the element or the node at index 6. I need that value 6. How can I get that value 6? Well, let's say we're at node 0 and then we go to node 2. Wouldn't it be great if I could store that 0 first? Store the 0 and then go to 2. Store the 2 and then go to 6. And that's when we get to the -1. Store the 6 and then get the -1. We're storing the previous pointer as we work our way through the tree. So let's have a look at that. Store the current search pointer and then update the search pointer. So it starts at 0, save that, and then it becomes 2. Save the 2 and go to 6. Save the 6 and then go to -1. So we should grab the 6. So let's print the prev pointer. Let's see if we've got a 6. Yes, we grabbed it. Okay. So take a moment to think about that line of code. Before we update the search pointer, we're just going to store what its value was or is. I've called it prev pointer. Maybe this is really current pointer. Anyway, it doesn't matter. Now that we've done that, we can update this value, can't we? We can say btree. We need a bit of logic here, don't we? We know that we're at 6, but we don't know which -1 we need to change to be 8, right? So we need a bit more logic. If new node dot data is greater than btree. Now remember, prev pointer is storing the index of the node that we're at. So that's what we're going to do. Prev pointer dot data If that's true, then btree prev pointer dot, let's just think about this again. If new node.data is greater than, that means we're going to the right. We're going to update the right pointer to be 8, which is basically the free pointer. Else, btree prev pointer, which is 6, remember, this is the node that we're currently working on, dot leftp will be equal to the free pointer. We've just inserted a node into a binary tree. And to test if we've done that, let's do this. Let's call my search function, which is going to return the index of a search value that we're looking for in the tree, or it's going to return -1. So for example, if I do this, print display, what's the name of this function? Display node index. Let's look for 13, just to test if this works. We should see the value 0. Yes. Let's do another one. Let's look for 18. 0, 1, 2. It should return 2. Yes, it works, okay. Now let's do the big test. Let's look for 33. We've just inserted it using this logic here. We've just inserted it into the tree. Let's see if we actually did it properly. We should get the result 0, 1, 2, 3, 4, 5, 6. No, 6, 7. It exists here, doesn't it? 8. The answer should be 8. 6 is 21. 8 is 33. So let's run that and see if it works. Yes, it works.